All right, good morning, everyone. Well, I don't know what time it is for you, but it's morning for me. We are going to do, we are going to start talking about the third case here in this world of solving ax equals x prime, where a is a 2 by 2. And this is the case where we have a repeated eigenvalue. Exactly like chapter 3. First we had R1 and R2 real, R1 not equal to R2, and we had 3 subcases there. And then the second one we had what? R1 and R2 equals lambda plus or minus mu I, so that the R's are complex. And now on this third one, we're going to have that R1 equals R2 equals R, a repeated root. Okay, so let's jump into this. So let's assume we're in case 3. So we're here now in case 3. I have some matrix A, like that. And the characteristic equation of A turns out to have repeated roots. So the eigenvalues of A are R and R. Okay, so definition. If an eigenvalue is repeated m times, we say it has algebraic multiplicity m. So in this case, R has, so in this case, R has algebraic multiplicity two, because it's repeated twice. As we'll see in the 3 by 3 and the 4 by 4 case, you can have triples and quads. So for now, we're just dealing with the 2 by 2. Okay, so as before, when you solve A minus Ri zeta equals 0, in this case, you get 1 or 2, but usually 1 eigenvector. The case where we have 2, I'll deal with later. But almost always we get 1 eigenvector for this repeated root. So here's another definition. The number of eigenvectors related to a given eigenvalue is called the geometric multiplicity. Excuse me. Okay, and it's always less than or equal to the number of eigenvalues or the algebraic multiplicity. So the geometric multiplicity is less than or equal to the algebraic multiplicity. Okay. So in this first case, we say R has geometric multiplicity 1. So we get one eigenvector when we do our row reductions. So let's call this what we've been calling all along zeta, so the vector zeta. Okay. So we get one solution. So one solution to the ODE is it's x1 equals zeta e to the RT. Why did I do that? Darn it. Come back here. There it is. I'm telling them how to practice. Here it is, the colors. That's what I wanted. So there's one solution. So following chapter 3, we did a lot of work there with reduction of order, and a guess for a second solution would be what? Zeta t e to the RT. All right, because remember in that chapter section, we had the one root e to the RT, and then we slapped a t on the side after we did a bunch of work, and it worked out. So x2 equals zeta t e to the RT is a guess, doesn't work. And it's a boring computation, and you just get that zeta equals 0, and you can't equal 0 and not 0 at the same time, so it doesn't work. So the better guess here is this. It's zeta t e to the RT plus some sort of extra vector here. We're calling it gamma e to the RT. Okay. And so here's a guess. It winds up working, but you have to see why, and it also tells you how to find this gamma. Okay. So what we're going to do is something we've done all semester is we're going to plug x2 into our equation ax equals x prime. To do that, we need the derivative, right? So we're going to do this. x2 equals x2 prime. All right, so we have, on the left-hand side, we have a gamma t e to the, a zeta t e to the RT plus a gamma e to the RT. And I'm going to try and make my gammas all blue, because that's what we're looking for. Okay, so I'll make my gammas blue here. So that's the left-hand side of the equation. Let's look at the right-hand side. I don't have a lot of space here, so I'm just going to put it underneath. So when I take the derivative, I have to do the product rule here. So I have zeta e to the RT plus zeta RT e to the RT. And I'm just taking the derivative of x2. And remember, the vectors are actually what? They're constants. Plus gamma r e to the RT. And I don't have enough big enough screen to make it all the way across, but we're taking the left-hand side and setting equals to the right-hand side. Straight away, you see that every term has an e to the RT in it, so we can divide them out and just have a matrix equation. Okay. So on the left-hand side of here, I have, so now I have, oops, I don't want blue. Now I have a zeta t plus a gamma equals, this is the fun one, zeta plus zeta RT plus gamma R. Okay. We're close. Check this out. This is super cool. If I equate the terms with t's in it, I have this guy and this guy. All right, so I have a zeta t equals zeta RT. Well, t is non-zero, so I can divide it out, and this says a zeta equals r zeta. This is key. This is the eigenvalue, eigenvector relationship, right? Zeta is the eigenvector corresponding to R. So this is a true equation, and if I subtract the two out, I get 0. So now I'm left with, right, so this guy cancels this guy. So now I'm left with A gamma equals what? Zeta I lost something. Oh no. Plus gamma R. I'm just gonna, oops. Been a while since I worked with this thing. Plus gamma R. Okay. All right, let's bring the gamma R over to the left-hand side here. So now I have A gamma minus R gamma equals zeta. Remember, zeta is what we found already. That's the first eigenvector. And now if I factor the gamma out of the left-hand side, I have A minus Ri. That's the identity matrix. Gamma equals zeta. And this is a matrix equation we can solve for gamma. So all that work led to this. I should make it like this so it stays, right? So that's what's new here. So when you find the second solution, so the first solution is zeta e to the RT. And the second solution is zeta t e to the RT plus gamma e to the RT, where gamma is found by solving this equation up here, A minus Ri. Oops, it's supposed to be a gamma. Equals zeta. Okay. So it's just a subproblem. And yeah, it's really cool the way it comes about, but this is pretty intense amount of work here. Okay, so let's do an example. E, G. We're going to let A be the matrix 1 minus 4, 4 minus 7. So the eigenvalues of A without doing any work are minus 3, minus 3. Well, I've already done the work, okay? So the eigenvalues of A are minus 3, minus 3. You get that from the characteristic equation, which is what? R squared plus 6R plus 9. And with a little bit of work, zeta, the eigenvalue corresponding to 3, minus 3 is 1, 1. So our first solution here is 1, 1 e to the minus 3t. Okay. So now to find the second solution, we solve. What do we solve? We solve a minus ri gamma equals zeta, okay, which is what? A plus 3i gamma equals 1, 1. What is A plus 3i? It's 4 minus 4. 4 minus 4. 4 minus 4. 1, 1. Which reduces to 1 minus 1, 1/4, 0, 0, 0. Okay, and this says that gamma 1 equals 1/4 plus gamma 2. Right? Okay, so writing that all out, and so in here this is implying that gamma 2 is free. So gamma equals gamma 1, gamma 2, which is equal to 1/4 plus gamma 2, gamma 2, which is equal to 1/4 0 plus gamma 2, gamma 2, and that's equal to 1/4 0 plus gamma 2, 1, 1. Okay. Now, here's the redundancy which happened all semester. This is zeta. So it's already counted in the other solution. So this guy goes away because it's redundant. And so this is gamma in all its glory. Okay, so what's the second solution? Here's the second solution. The second solution is it's 1, 1 t e to the minus 3t plus 1/4 e to the minus 3t. And so the general solution is C1x1 plus C2x2. Now, here's a little thing. If you write the whole thing out, I hopefully have enough room here. It's C1, 1, 1 e to the minus 3t plus C2. The C2 goes over the whole terms. There's not a C3. Students get confused about this, right? So that's your general solution. That's your general solution. Here's x1, and here's x2. Okay. All right. I have a guided practice for you to do at the end, but the phase portrait is pretty cool. So let's get into it here. Let's get into it here. Because this is my favorite part. Get the whole screen here. X1, X2. we know the only eigenvector here is, because it's geometric multiplicity 1, is 1, 1, right? So where are the colors, darn it? Not as good as I used to be at this. There it is. I'm going to make my eigenvector purple. Okay, so here's the eigenvector 1, 1. And because r is negative, this thing is pointing into the origin because solutions are converging to 0 as t goes to infinity. Okay. Right? Now for the good part. We don't get a second eigenvector. We get, we have to figure out this phase portrait. So here's what you do. You go back up here and you take out the e to the minus 3t from all these terms. That basically tells you that this thing is converging to 0. And what's left is this. C1, 1, 1 plus C2, 1, 1 t plus C2, 1, 4, 0. This is, I'm gonna do it like this is just a line. This is a line on this graph. Okay. And all the trajectories converge to 0 parallel to this line as they come in. So how do you do that? Here's how this goes, and I love this. So you're gonna pick. Just start easy. I'm going to pick C1 equals C2 equals 1, okay? I'm just picking these to get a reference point. So when I pick that, I get 1, 1 plus 1, 4, 0 plus 1, 1 t. This is a line, right? So in particular, it's the line 1, 1 t plus, what's that, 5 force 0. Right, and this is y equals mx plus b. Okay, did I do that right? Yeah, 1 plus the fourth is a 5 force, and 1 plus 0 is 1. Ah, I didn't do that right. Glad I checked. You probably saw it before I did. All right, I had this guy to this guy, I get 5 force. I had this guy, I have 1. Okay. So here's what you do. You set this thing in motion. Let t equal 0. And I get the point 5 force 1. Put this in what color? Green. Okay. That didn't get me far enough away, so it's too close to our thing here. So let's pick some different C's. I should have done this before. Sorry. I'm gonna let C2 be 2. C1 equals C2 equal 2. So go away, all of you. So now I have 2, 2 plus 2, 2t plus, actually I should let it be 4, shouldn't I? Most of the time 1, 1 works, but this time it took me too far away from, too close to the origin. You can't really get a feeling for what's going on. So sorry for that. we're letting C1 equal C2 equal 4. So what I'm left with here is 4, 4 plus 4, 4t plus, what, 1, 0. That's a nice line. Right? And so when you clean this up, you get 5 fourths plus 4, 4 t equals y. It's not much better than what I had, darn it. Okay. Anyways, let's put this in motion. Let t equal 0. And you get the point 5, 4. 5, 4 is about right there. Okay. So that's where t equals 0. Okay. Now let t equals 1. So we get 9/8. Okay. So 9/8 is going to go, and it's going to go, what? It's going to go in this direction up to t equals 1, 9/8. So now we have direction. So here's the thing, and here's the cool part. As I'm going to infinity, I'm going like this, going in this direction. But as I get close to infinity, I have to come back to the origin. So what happens is this guy goes up and comes back around like that. Let me get some better colors here, right? So here's my trajectory. It goes like this. It's heading off to infinity in this direction, but at some point, the e to the minus 3t takes over and sends it back home. So all of them are going to look like this. And once you get the one side, you get the other side for free. Voila. Okay, well, that was fun. Hopefully it wasn't too hard to follow. Here's your guided practice. Let A be, where is that sucker? Minus 3/2, 1, minus a 4, minus a half. As you can see, this thing, the x equals 0, is asymptotically gotta spell it out. Asymptotically stable, and it's an improper node, is what it's labeled as. Okay. I'll show you what a proper node looks like in class. All right, so have a go at this guided practice here. I think the roots are 1 and minus 1 and minus 1. What did I get? I don't know, you'll figure it out. And I'll see you